So let's think of these principles of absorbance and emission spectroscopy in terms of the hydrogen atom. So what's shown here on this slide, right, is on the top the emission spectrum for the hydrogen atom, and the bottom is an absorption spectrum. So what you see in the emission spectrum is several bands of light with given energy, right? And you'll see that they are very discrete bands, very like you can well define them, where they light up in there. And on the bottom, the absorption spectrum, right, we see these dark gaps within the wavelengths of light shown here. And you can see that the bands in the emission spectrum correspond with the gaps in the absorption spectra shown below. So what this indicated is that the hydrogen atom could only absorb light at discrete energies, and that those corresponded with the energies that could be emitted from an excited hydrogen atom. And so this gave some clue experimentally as to how electrons are arranged within the atom. And so the first thing, before we discuss how that is possible, right, we need to discuss the Rydberg's equation. And so those energies right, were found to abide by a mathematical formula known as Rydberg's equation, which said the wavelength, 1 over the wavelength of the light that was absorbed or emitted, is related to R, which is called the Rydberg's constant, times Z squared, okay, which is the charge of the nucleus. So for hydrogen, the charge of the nucleus is 1. There's only 1 proton in it. Times 1 over N1 squared minus 1 over N2 squared, okay? Now, these are referred to as principal quantum numbers. And importantly, these can only be integer values. Positive integer values, I should say, right? So 1, 2, 3, 4, 5, etc. And so the behavior of these absorption and emission spectra were satisfactorily defined by this equation. And so the last thing I need here is, of course, what R is. So R is Rydberg's constant, and that's 1.097 times 10 to the 7th per meter, okay? And so remember, we're talking about energies here, so this is all related to 1 over the wavelength, but remember that this is related to energy because energy is equal to hc over lambda, okay? So in a way, we are looking at the energy of these wavelengths, but we're just using 1 over lambda as a proxy here.